talk about Tulip. This is absolutely not the same talk I gave at PyCon. No, I'm serious. I wrote a completely new set of slides this afternoon, and the order and everything I'm saying is different because a lot has happened since March. Before I begin, thanks to my sponsor, Dropbox has very generously let me work on this for a lot of my time since I joined. So I have this, I like this sort of organ pipe arrangement of text. I like to arrange my imports that way too. So I have a little bit of philosophy about asynchronous I/O. I'm actually going to say some woolly, soft stuff about the road to Tulip, how I approached the project, sort of with the goal of success. Then there is the sort of whole lot of technical stuff about the architecture of Tulip. And if there's any time left, which given my track record there won't be, I can show examples and we can do Q&A. I would probably do the Q&A first. So let's see what we have about asynchronous I/O. What is asynchronous I/O? Clearly opinions differ. I mean, to the point where when I finally sort of started thinking about we're going to have to put this in the standard library. I want it in the standard library, and I do not like things in the standard library that queued names. So even though I love the name Tulip for the project, I do not want the module that you import in once it's in the standard library to actually be called Tulip. So I thought, well, what should we call it? I like boring names that explain what it is, so I proposed to call it Async I/O. I think there was one prior proposal that was somewhat similar. And immediately Glyph wrote a novel about why asynchronous I/O was the name that, you knew this was coming. Why Twisted had been using the term asynchronous I/O, and he has started hating that particular term more and more. But there wasn't anything that sort of could be abbreviated more easily, so I'm still calling it asynchronous I/O. But then what is it? Is it using your file descriptors in a non-blocking way? You can do that with Python standard library socket since forever. Does it mean using callbacks like people like to do in JavaScript? Well, when does your callback get called? Does it get called when your operation is done, or do you get a callback when it's actually the I/O system is ready for your operation? There are different approaches to that. Threads actually are something that can legitimately be considered as a very good solution for certain types of asynchronous I/O. It's a very sort of rock solid abstraction. The only problem is that there are a few systems where you can actually sort of open 100,000 sockets and have 100,000 threads to manage them. So that's where people want different solutions, and that's where sort of it all breaks apart because there are too many different ways of doing it. Gvent, Tornado, Stackless, Twisted, what have you. So I always like to go back to fundamentals, see if I can forget all those years of sort of history and partial solutions, and then sort of after I've analyzed what the problem is and how I would solve it, I'll still check in with what the experienced practitioners have done. So look at what is asynchronous I/O in units. What's the sort of the best way of doing it? You use select or any number of APIs that have grown to replace select and to be better in some way. On the other hand, on Windows, the select exists, but it's pretty much a toy. Well, a lot of Python scripts are toys too, so that's actually a great match. But if you want to do serious stuff on Windows, you have to use something else, which is called IOCP. I think it means I/O control ports, and who cares? It's called IOCP. But the key thing is that these two paradigms, using IOCP or select or poll and friends, these two paradigms are completely different. And that is because they have very different DNA. Sort of, I think IOCP, in my sort of view of history, IOCP actually goes back from mainframe I/O from even before BSD invented select, but that's just my personal opinion, and I'm not a historian. Anyway, if you are using select or any of the sort of more modern variants that really sort of have the same functionality in a slightly different API, you say, here's a bunch of file descriptors, block until at least one of them is ready, or maybe until timeout. Once that blocking call, because the select or poll call really is a blocking call, it sort of can stay away for minutes if there's nothing happening on your file descriptors. Once it says, okay, this file descriptor is ready and this one is ready, you can attempt your I/O. Now there are still situations where that attempt will still fail, so you still need to use non-blocking mode. But that's the fundamental operation of asynchronous I/O in Unix. And so on Linux, the right way to do it is epoll. On OS X and BSD, the right way to do it is KQ. I haven't actually found any platforms where poll is still the right way to do it. I mean, if poll doesn't really have many advantages over select when you're using it from Python. However, on Windows, as I said, select on Windows exists, but it's really a toy. I don't know how many file descriptors it handles, but maybe 50 or so at most. So the real way to do asynchronous I/O on Windows is this IOCP thing, which is also called overlapped I/O if you read the official Microsoft documentation. And so this gives you an actual honest-to-God callback. It calls a function. It's not a blocking call. It actually calls a function. And you have to, there's a complicated way of arranging for that function to be called. But that function is called when the I/O is done, when the bytes that you were reading are actually in your buffer, or when the bytes that you had in your buffer that you wanted to write have actually been transferred into kernel space. I think what sort of happens to those bytes after they're in kernel space is none of your business. So this is a really high performance approach to asynchronous I/O, just like epoll and KQ are, and it's very different. You have to use it on Windows if you want to sort of write a scalable server. So what can you do? How can you unify those completely different paradigms? Obviously, you have to come up with the right abstractions. And it turned out that if you sort of think about it, the proper abstractions are very close to what were called protocols and transports in Twisted, and that's what we're calling them in Tulip. And I have much more about that in the architecture section. So, okay, now for the woolly, soft stuff. I had a bunch of goals. My original goal, and it's actually, I think yesterday was the 1-year anniversary of the discussion about Tulip. That's when I sort of started posting on Python Dev saying we got to do something about asycnore. We can't just sort of make a small upgrade to it. We got to just throw it away, forget it ever existed, and come up with something real. So that was my first goal. Then sort of, if we're starting over, if I'm going to put this much effort in and I want something that's future-proof, I want it to sort of still be useful 10 years from now, say until Python 4 or so, which I always use as a nice horizon, because after Python 4 begins, I'm retired. At the same time, I want it to be usable today. I don't want this to sort of be only the future of asynchronous I/O. I also want it to be the present. Then Python 3.3 actually introduced this wonderful new feature by Greg Ewing called yield from. It's PEP 380. It's a real shame that it didn't make it into Python 2.7. The world might have looked very different, but it didn't. It did make it in Python 3.3. It's a wonderful thing. I'll try to explain more about it, but it's kind of magical. But it's new in Python 3.3. I decided I wanted I wanted to write I/O handlers using yield from instead of as callback functions. That was sort of one of my goals. So I'm sort of stuck with Python 3.3 as the present. But I mean, various people said, well, yield from is an ugly spelling, let's give it a different name, or there are a bunch of details that ought to be different in the language, or the event loop really ought to be integrated into the system. So there were sort of suggestions. If you're starting all over with asynchronous I/O, build it for Python 3.4, and I thought that's unacceptable. I wanted to be working with the Python version that exists now, which was Python 3.3 at the time. And so the plan is actually to have a third-party release on PyPy that will work with Python 3.3, and also to have it in the standard library in Python 3.4. So it can use any feature that's in Python 3.3. It cannot use any new features unless they can be re-implemented inside Tulip in pure Python. Now the final goal, which sort of, I wasn't aware that it was an important goal right from the start, but which became a very important goal after I started soliciting expertise from various people who clearly knew more about this topic than I do. I want some kind of interoperability with third-party frameworks. Let's not use the word legacy. So what do I consider interoperability? Different frameworks being usable together in the same program, in the same process space. So say you import Tornado because you want to write a web server, and you import Twisted because you also want to have an IRC interaction as part of your service. How do you tie those together? Well, they somehow have to share an event loop. And the hope is that through adaptation, they can either both use the standard Tulip event loop, or one of them has their own event loop that is adapted to the Tulip style. And one way or another, you can actually write some part of your application in Tulip style, part of your application in Twisted style, part of your application in Tornado style, and you can smoothly transfer between all three. So that's a pretty tough goal to meet, but I'm hopeful that I've solicited feedback from a lot of different people who have third-party frameworks, and actually several people have already written a prototype of an adapter or a Tulip version that talks to, for example, Qt or Tornado or a few others. So there are also lots of things that I sort of really don't think ought to be a goal. It doesn't have to be perfect. In fact, if it's too perfect, it's not extensible, so that I don't like that so much. It doesn't have to be everything to everyone. I don't want it to actually replace the third-party frameworks. It's going to be a framework of its own. I mean, and there are other situations. I mean, for some situations, once something ends up in the standard library, that's it. Nobody's gonna write another strings module or something like that. On the other hand, for other types of applications, having something in the standard library is not necessarily a reason for people to stop developing similar things. An example is actually GUI toolkits. I mean, we still have tkinter in the standard library and still being used for some important stuff, but clearly people also write other GUI libraries. I also, in the end, decided not to have specific protocol implementations like HTTP or IMAP or SMTP or FTP or whatever as part of the Tulip implementation. That was just, there are too many protocols, and it would sort of blow the size of the project completely out of proportion, and it's big enough already. And so I already mentioned I really don't want to compromise the Tulip code base to somehow support older versions of Python. Even Python 3.2 is just, it would mean that nowhere in Tulip could there be a yield from statement. So that's too much. There's a mailing list. There's a project repository. Everybody can see everything that's going on the mailing list. There's no moderation. Everybody can submit bugs to the issue tracker, watch all the code check-ins. I like small, frequent commits, so there's lots of junk in the repository, but you can analyze that and follow my thinking in some cases, and you can certainly sort of learn why things are done a certain way and figure out whether a particular line of code was a mistake or very intentional if it isn't documented. A lot of time meeting in person with various people. I visited Twisted, Twisted visited me. I had a Skype session with Steve Dower from Microsoft. I forget if I met with Ben Darnell, but we had long email exchanges about this topic. Various other people also did a lot of sort of in-depth consulting about what they thought was right. And I've got for a project this young, I've got a fair number of contributors and collaborators. Nikolai Kim is here, who wrote a lot of the unit tests and is still debugging the code as we speak. And so in the end, I really had to keep an open mind. I probably went into this thinking that, oh, I know how select works. I can figure out how KQ and epoll work. I can write my own asynchronous IO library in a month or so. I learned a lot. I had to change my mind. At some point, ironically, when I was disconnected from the internet completely, I did an in-depth analysis of how deferred in Twisted actually works. I wrote it up, and I think I got a gold star from Glyph. And still, I think I didn't lose my way. It's not just Twisted rewritten in PEP 8 style. More goals. It needs to support all major platforms where Python runs. So at this point, it's basically Unix, Windows, and OS X. Of course, it needs to support IPv4 and 6, TCP and UDP, although UDP I'm not much of an expert at, but for Bram Cohen, who I think he's also here, gave me a lot of useful tips on how UDP is actually supposed to work. That was another really great expert opinion I got. We're still, if you follow the list, you can see that we're still struggling with SSL, but it must support SSL, and it must do that using only what's available in the standard library, which is a kind of crummy module named SSL based on OpenSSL. It doesn't do everything right. There are good reasons for that, but it still doesn't do everything right. We're gonna do the best we can. And through sort of, hopefully third parties can write their own transports that will work better and that people can use if they need more security or more flexibility in that area. It also supports pipes and sub-processes. And on Windows, it even supports named pipes. So I think I already sort of mentioned this extra goal. I don't want to depend on other third-party software, just the standard library. Otherwise, sort of, you can't stick something in the standard library when it depends on a third-party thing. So then once it starts depending on third-party code, it is third-party code itself. I also didn't like to have to write more C code for this. The only extension was necessary was the IOCP support. I suppose we could have done it with C types, but that really was too painful. So there is a fairly small one single extension module that is only needed on Windows that does the overlapped I/O for you. Well, then the final goal that sort of slowly emerged was, I may love yield from, but not everybody loves yield from. And so it must be possible to use yield from, and it must be supported well, but at the same time, especially at the interoperability level, yield from is not the focus of the API. The callbacks, which are just standard Python functions, are actually the approach to the road to interoperability. So Tulip is actually a large library. There are lots of moving parts, and they're sort of, I like to think of the three visible parts of it. The first part is how to write callbacks without writing callbacks. And that's done through things called coroutines, which are really just generators that use yield from. And also through objects called futures, and you can wrap a coroutine in a future, and then it's called a task. Did I mention I don't like callbacks much? A second big component of Tulip is an event loop. There is one event loop typically in a program. In a multi-threaded program, you could have multiple event loops, one for each thread. But that's pretty specialized, and there's actually a policy that sort of tries to discourage that a little bit without making it impossible. The final thing is transports and protocols, and that's where all the actual I/O happens. I mean, if you're connecting to a socket or an SSL connection, you're using a transport and a protocol. So let's have a look at each of these in turns. Let's start with the coroutines and, oh, great. Hey. I know that I want to recover my work because I don't think I made any changes. Well, that was the example that I was planning to show, by the way. So there's the coroutine decorator. There's a function. You can pretend that this is just a sequential function. You open a connection. The yield from just says wait until it's actually opened. Then, well, that's just a debug statement. You write a string to the connection, and then you read the headers. And so reading is a blocking operation. Writing is not actually a blocking operation. And at the end, you read all the rest of the data from the socket, and that's the body of your HTTP request. Okay, so, yeah. As you could see in the example, a coroutine is really just a generator function. And actually, in most cases, it's not absolutely mandatory that you put that coroutine decorator on there. Now, I would strongly recommend to always put it on there because it helps the human reader of your code. There are also some end cases where if you don't put it on there, it suddenly, the compiler doesn't know that it's a generator because there's not actually a yield in there anywhere, and then it would behave completely different. The essence is that in most of the time, that coroutine decorator just returns the decorated function unchanged. It doesn't actually wrap it in another layer of function calls. So that's what a coroutine is. And so really the magic of coroutine is not in how it works, but how you use it. And that's what I showed in that example. So future is an honest-to-God object that has an interface that I can control. Now, of course, yeah, a generator is also an object, and it has an interface, but I can't control it because the interface is very minimal and built into the language. On the other hand, the future is an object that's it's an actual Python class, and I can define exactly how it works and how it behaves and when it gives you an error and so on. Finally, a task is a variant of a future that wraps a coroutine, and we'll get to that. So, okay, here's the version of the example that I wanted to show. So again, you open a connection. Yield from basically just means wait until that connection is actually ready for you to use it. I mean, that's like TCP connection setup. I don't even know exactly what goes into TCP. It's been a long time since I read that book. One of the things it also does is name lookup, which also is a blocking operation because you may have to go out to some DNS server on the other side of the world. So every time where in that function it says yield from, you can pretend that there is no yield from and that the whole function is just some sequential bit of code that executes one step at a time. You don't have to think about, well, okay, if all I have is callbacks, how do I write a loop that reads one line at a time, blocks until it has that line, and then sort of goes back to the next line, and then there's some sort of end condition where at some point you fall out of that loop and you do something different. You can do that, you can sort of schedule another callback, but in the end you end up with a lot of little functions that each represent sort of one part of the function between where the start and the first yield from, or between the first and the second yield from, and so on. And then you, as the human reader, you have to piece all that together to figure out, well, what's this code actually doing? Or more likely, where is my bug? And just to show that they're just functions that call each other, here's another coroutine that just calls the first coroutine. It yields from the first one. So at this point, this sort of instantiates the generator. The yield from then waits for all this code to execute. All these blocking things are also blocking here. Finally, when this thing executes a return statement, that value returned actually becomes the return value of yield from, which is really an expression. And then it prints it to standard out. So I think that I'm pretty sure that that code as written here would actually work if you have a reasonably behaved HTTP server. But I don't remember the password for the Wi-Fi network, so we're not going to show it. So the one sad thing is I could stand here with a whiteboard and draw diagrams until I see blue in the face, but I don't think I could really sort of convey an understanding of what happens here. There's a trampoline involved, and the generator implementation is super complicated. There is like 50 lines of pseudocode in PEP 380 that try to explain what the exact precise formal semantics of yield from are. What happens when you throw an exception in, because if you throw an exception in on one end, it comes out all the way on the other hand. If it doesn't get handled at that point, it bubbles up through the stack, one stack frame at a time, and everything sort of makes sense if you pretend that the whole thing is just sequential code. If you end up with that thing printing a stack trace, just the standard Python built-in stack trace, it will actually print the stack trace you would expect if it was just sequential code with no yield from in there. So I really recommend sort of on first reading of coroutine code, just pretend the yield from isn't there. So futures are something completely different. A future doesn't have any code running in it. It's not like a generator that sort of represents blocks of code that are running. A future is just an object that either has a result or it doesn't yet have a result. Now, it could also have an exception instead of a result, but that's like any other expression or value in Python. If you call a function, it will either return a value or it will raise an exception, and that's exactly what a future can do. Now, these futures are almost, but not quite, like the futures defined by PEP 3148, which is in Python 3.2 under the name concurrent.futures.future, which is that name is a little too long for my taste, but I accepted the PEP anyway. So what can you do with a future? Well, very quickly, you can set its result. You can only set the result once. After you've set it, the result will never change. You can ask for the result. If you ask for the result before it's been set, you get some crazy exception that says, stupid, you shouldn't be asking for the result yet. You can also, instead of setting a result, set the exception. Again, once you set the exception, that's it. After that, you can't change the thing again. If you want to know whether it has an exception or a result, you ask for its exception. That's actually a method. Yeah, I definitely lost some of my changes because it's supposed to be f.exception. So f.exception returns the exception object if there was an exception set, or it returns none if there's no exception. And if it returns none, then you can call result. You can also add callbacks to a future. That's something you probably don't want to do, but because Tulip already does that for you. There's also something called cancellation. Don't worry about that now, although it's been a huge discussion, and that's actually my investigation on deferred made me completely change my thinking about cancellation. Two important inquiry functions. You can ask whether the future is done. If it's not done, you shouldn't be calling result or exception because they will fail. You can also ask whether it's canceled. So what elephant in the room have we not talked about yet? Well, you can use yield from with a future. If you have a future and you somehow arrange that at some later point in time, somebody else is going to call set result on that future, and that somebody else must sort of be cooperating with the event loop, then if you want to wait until that future has a result, you just say yield from that future, which is almost the same. Again, if you squint, that's the same as just calling its result method, except that the result method doesn't block. It either gives you the result if there is one, or it fails if there isn't one. But yield from the future, so not yield from f.result, but just yield from f, passes control back to the event loop until the point when the future actually gets its result set. So essentially, as soon as some other task or coroutine calls set result or set exception on that particular future object, your yield from will complete and pass that result to res. Or if they called set exception, that whole yield from will raise an exception. So essentially, now you can sort of use this as abstraction. You can use either a coroutine or a function that returns a future. And from the caller's perspective, if you use yield from on that function, you don't care whether it's one or the other. And so the author of the software is actually able to, in one version of the software, have that thing be a generator. In another version of the software, have that thing be a future. And in Tulip, actually, for various internal APIs, I've gone back and forth between the two. And there's very little code you have to change when you do that. So that first, this is not how you normally write your code. You never instantiate future. You just call a function, and by prior arrangement, that function will return a future, and that future will eventually become done, and then your yield from will continue. Or if that the thing that was computing the result encountered an error, it can call set exception, and then your yield from will raise. So now, what's a task? Okay, a riddle wrapped in a mystery inside an enigma. Well, actually, that was Churchill about Russia. So what is it? It is a coroutine wrapped in a future. Task is actually its own class, but it's a subclass of future. And wherever you can use a task, you can use a future. Wherever you can use a future, you can use a task. From the user's perspective, that if something or someone gives you a task or a future, you shouldn't have to care which of the two it is. And you shouldn't even have to care whether it's a generator or either a task or a future. So you can use it in exactly the same way. And again, so that means it works with yield from, of course. On the other hand, if you wrap a coroutine inside a task, there is one thing that differs, and that is if you're waiting for something else, the task can still make progress. So this is how you introduce actual concurrency or parallelism in your application, by using tasks. On the other hand, if you're using a coroutine, the coroutine, because it's actually really just a generator, and because of that thing I couldn't explain, the coroutine just sits there waiting for you to wait for it, and it doesn't actually make any progress. So there you have it. You can wait for all kinds of things using yield from, and the implementation of the thing you're waiting for has a lot of freedom. So I guess I already mentioned exceptions. They all can raise exceptions. The one nice thing is if you wrap a coroutine inside a task, when the coroutine raises an exception, that calls set exception on the task, which is really also a future. And of course, because when you're waiting on that task, that exception that you just set will be raised. So that in effect, again, the exception bubbles from the coroutine to whatever coroutine is waiting for it. And we arrange for that to also give reasonable stack traces. Now there's one final thing. If a task fails in the wood and there's no one to listen to it, we worked hard and we introduced a helper object and a destructor method, and it will log the trace back for you. And it does fairly little overhead when you you actually do wait for it. We don't pre-compute the traceback as soon as the exception gets raised. We only extract the traceback from the exception object if we find out that the task is being garbage collected. On the other hand, if a task succeeds with a valid result and nobody looks at the result, we don't really care because that's sort of standard Python. If you call a function that returns 12, but you don't print that value, you don't use it in an if statement, then that's fine. And there's a sort of another edge case, if you create a future or a task and it never gets a result and you never wait for it, then we also don't care. There's one final case where, unfortunately, we're not so lucky. If you call a generator and you never wait for it, then it doesn't make any progress, and we have no way to attach something that logs that. I mean, that would actually be a reason to, at least in some cases, put an extra wrapper in the coroutine decorator. So, a completely different topic, the Tulip event loop. What's an event loop? It multiplexes different activities. And in the Tulip case, the activities that are being multiplexed are various callbacks, like call something soon or call it at a particular time or after a certain delay. There's also I/O callbacks. You can register something that says when this socket or pipe file descriptor is ready for reading or writing, call my callback. That's part of that's taken care of by the event loop, although the hard work is actually done by the selectors sub-module, which was sort of introduced for Tulip and is now also in the Python 3.4 standard library. There's signal handling there if you really need to on UNIX. There's also a little bit of interface with threads. And another important part of the event loop API is whenever you actually want to do high-level I/O, so you want to use protocols and transports, you normally do that by calling a method on the event loop. Although if someone writes a custom transport, they don't have to add a method to construct that to the event loop. You can just have a function too. But by convention, all the built-in interfaces for constructing various types of transports and protocols are methods on the event loop. So I try to come up with the simplest possible API for scheduling sort of plain and timed callbacks. You could say this is not minimal because call later and call at can be transformed into each other, but it turns out that depending on how the event loop is implemented, one or the other is more basic. And they're sort of, that doesn't really matter. You could also get away with without call soon because you just specify a zero delay, but it's actually very common to have to schedule something to be happening sort of at the next tick. So this is not actually minimal, but it's still pretty small and clean. You can also you ask what is the current time. It actually uses time.monotonic if it's available. So that it has nothing to do with the actual time of day, but it is a nice, reliable clock. Notice that there is no way to set up a repeated callback because at some point I had that, and then someone started saying, oh, but the repeated callbacks need to work in a different way. And then someone else said, no, there's my favorite event loop library has a different type of callback, and there are actually 3 different kind of timers, and some are synchronized and some have a sleep. And I said, okay, well, I'm not going to add 3 different timers. I'm not going to choose which timer. You can easily implement every kind of repeated timer you want yourself using just having a callback that calls call later again. So do it that way. Nobody has complained ever since. If you're writing a transport, and that's really the only time that you should be using these APIs, you can say, for this file descriptor, when it becomes ready for reading or writing, call this callback with these arguments. Reading and writing are treated separately. There can only be one handler or one callback per file descriptor for each direction. You can just remove them by specifying the file descriptor. So do not use this. Also, if this is all you need, if you don't care about event loops and protocols and all the other nice stuff, you can just use the selectors module and write your own asynchronous framework. And the nice thing about the selectors module is that it actually chooses intelligently between KQ and epoll and any other fallback approaches. So if you really need to handle Unix signals, you can do that with a similar API as the IO callbacks. Threads. It would be nice to say when you're using Tulip, you never have to use threads again, but that's just not true. There are certain third-party APIs, even some standard library APIs like getAtterInfo, which goes out to DNS, so it's definitely a potentially block and call. There's no asynchronous API to that in the standard library. I really don't want to write my own DNS client. I didn't want to sort of require a change to the standard library. So in the case of name lookup, there's a very simple interface where you can say, run this particular function in a different thread. And there's a little thread pool based on PEP 3148 called Executor. If you think you're going to use this a lot, you can configure that thread pool or that executor. When you're in a thread, if you're not using this mechanism, because that's sort of, the run-in executor does everything for you. It actually returns a future that you can yield from, which blocks until that thread has actually called the function and gives you the result or the exception. If you're writing your own thread machinery and somehow you start a thread and you give it some stuff, you put something in the queue, now you're running in the thread and you want to call a callback on your original event loop. You can't just call soon, because that thing is not thread safe. There's a race condition in there. So you have to call soon thread safe, which writes a byte to an internal pipe that wakes up the select call. Okay, you of course, since it's an event loop, you have to be able to start it and stop it. Normally, the only time you start it is in your main program. You say run forever. If you insist on stopping it from inside a running task, you can stop it by calling stop. We're considering actually making it sort of semi-illegal to call that, in the sense that some event loop implementations may not even have a stop. I don't want to go into too much detail there. There's also a special case which is very handy for unit tests and stuff, where you say, run until a particular feature is completed. So you can create your loop, but not run it yet. Then you can call some function that returns a feature, or actually you can also use a coroutine there. And then you say, now just run my loop until that feature completes. And this, just like all the other things, if the feature completes by raising an exception, run until complete will also raise that exception. There's one important thing that sort of keeps you from using this too much. You cannot start the loop when it's already running. Some event loop mechanisms are very proud of the fact that they have recursive event loops. Others do really not work well when you try to run an event loop inside an event loop. For I think for maximum interoperability, Tulip does not allow you, and it actually enforces that you don't start the event loop when it's already running. So basically, the only place where you should be using this is either in unit tests or in your main function. So how do you get your event loop? Well, there's a function in the package called getEventLoop. Gives you the current event loop, if there is one. If you want to play games with event loops, you can set the event loop. If you set it to none, then getEventLoop will also return none, and so then you no longer have an event loop. There's actually a whole bunch of APIs where you can optionally pass event loop objects around, so you never actually have to call getEventLoop. Tulip tries very hard not to ever call getEventLoop internally. It always already has a loop object, but you can sort of write code in either style. So how do you actually get an event loop? How do you bootstrap this? Well, if you just run your main thread, the first time you call get event loop, if there isn't one, it will actually create one for you and use that and keep using that. On the other hand, once you call set event loop none, that feature is gone. So there's one more thing I wanted to say, which is that if you have multiple threads, only the main thread has a default event loop. If you're sort of using multiple threads and you want a different event loop in each thread, you're going to have to sort of be aware of that you're doing crazy stuff and call new event loop in each thread and call set event loop with it. So, because not everybody agrees on this, sometimes the event loop is actually created by the system and it already exists and is already running by the time your code gets control. There's actually something called an event loop policy. And there's not totals all the way around. There's no event loop policy. The event loop policy is just a global object. You can actually set it with set event loop policy. You can subclass the default event loop policy to create your own policy. Nobody ever reads the event loop policy except the implementation of get event loop and set event loop call get event loop policy, and then they call the get event loop or set event loop method on that policy. And new event loop is also a method on there. So that's sort of basically any object that implements get event loop, set event loop, and new event loop can be an event loop policy. So this is the default policy. Whoops. Hello? Did I have a default? Okay, this is the default policy. There's only one event loop per thread, and only the main loop has a default event loop. Other threads, you sort of already said that. Okay, well, now we're officially in overtime. But I really do want to say a few things about transports and protocols because it's a really powerful, important abstraction. A transport is an abstraction that represents the sort of the socket end of a network application, whether it's a client or a server. The transport is the thing that sits between you and the socket. And of course, the socket is the thing that sits between you and the network hardware, and so on and so forth. But the transport is the closest to the socket from the application's perspective. The protocol, on the other hand, represents your code. So even though it looks like, I keep saying transport and protocol as if they're like almost interchangeable, actually, there are only a small number of transport implementations, and it's rare that you write a new transport. It's certainly possible. It's a well-defined interface, and you can do it. But you rarely have reason unless you have like a whole new kind of network connection that you want to support. And that's actually what transports are for. For example, IOCP has its own set of transports to use for various kinds of connections. And the IOCP transports have completely different implementations from the select or K-pol EQ based transports. On the other hand, in many cases, as an application author, it makes sense to write a new protocol class. So there's lots of protocol classes. The unit tests have like every other test defines its own little protocol class. So that's something that you do a lot. And transports and protocols are really closely sort of connected. So before I show what transports and protocols actually look like, how they call each other, let's make it clear that a transport is both used for a server-side connection and for a client-side connection. So if as an application you want to act as a client and make a connection to some other server, you call create connection, and that sets up one transport and one protocol for that particular connection. On the other hand, if as an application you want to be a server, and now of course you can be a server and a client at the same time, you can be many clients if you have a web crawler, but sort of for the particular case where you want to be a server, you call create server. And that sort of sets up a special server socket. It binds it and does all the sort of listen and accept magic. There's an accept loop, and then it will create a new transport and socket pair every time it accepts a connection. So when something happens to the transport, it will call a method on the protocol, which you can think of as a callback, even though I don't like callbacks, but here they are. They're there for interoperability. So the life of a protocol is very boring. Connection made gets called exactly once. Then data received gets called 0 or more times. Then maybe EUF received gets called. And then definitely at some point connection lost gets called. Connection lost gets called either with an exception or with none as an argument, depending on whether the connection was closed sort of cleanly and nicely, or you closed it yourself and everything was cleaned up, or you tried to write and suddenly the other side said, forget it. UDP also uses transports and protocols, but the actual APIs are a little different, and same for pipes and subprocesses. On the other hand, the protocol can call the transport, and from the protocol, the transport mostly represents the right end of the connection. So reading happens whenever bytes come in, the transport gets them first and then passes them onto the protocol by calling a protocol's callback. On the other hand, when the protocol feels like writing, it calls the write method on the transport. So that's not considered a callback. There's also this strangely named thing, write lines, which is really just write with a list of bytes objects. You can also write an end of file, except if the transport doesn't support it, which unfortunately is the case for SSL. But if you're not using SSL, writing an EOF is sort of, it closes the right end of the connection without, but you can still read more data. And that's sort of, there's an end case in HTTP and many other older protocols where that's necessary. And of course, you can close the protocol. Again, UDP is a little different. Now, the transport, because it represents the socket connection, has all sorts of other stuff. It actually has an inquiry method that you can ask, does write EOF actually work for this particular transport or not? You can also ask for all sorts of other extra information, like, okay, I just want to know what the socket is. You don't ask for the socket attribute. You call get extra info and you say socket, and then if it actually is a socket-based transport, it will give you a socket object. And if it's something else, it might not give you a socket, because if there isn't one, there isn't one. And if you panic, you can abort the connection. That throws away any buffered data that hasn't been written and closes things. There's flow control, was not yet implemented, so I'll pass on that. But we do have agreement on how to implement it, which is another major personal development item for me. So if you have to ask, the answer is no. These are not coroutines. The callbacks are not coroutines for interoperability. They're just, the protocol methods are plain callbacks. We do a little trick with the event loop in some cases, so that when one of your tasks is already active, the transport can't suddenly call you back. But when the transport suddenly decides that it has to call you back, it actually uses the event loop's call soon mechanism to schedule that callback at the next tick. When you call a method on a transport, that's just a method call. Now, how do you use the nice tasks and coroutines? How do you write that nice simple code? Well, you use, for example, the higher level API open connection. Notice that there is create connection and there's open connection. Maybe we need to rename open connection to something that's even less similar than to create connection, because it actually has a different signature. And open connection is the thing that I showed in the example and that you should be using if you want to write a nice simple coroutine or task. Create connection is what you're using if you want to use the raw transports and protocols. Miscellaneous, well, turns out sometimes it's useful to implement queues and locks. And so I mentioned the streams, which are the higher level interface. Man, this really is the wrong version of the talk, but I'm stuck here. So I'll just let you ponder a few things. Why shouldn't you be using threads? Why don't I like callbacks? What's wrong with microthreads? I haven't have a sort of a rant of an hour about that, but I'll withhold it. Why is yield from so much better than yield? Not everybody agrees on that. What's so cool about transports and protocols? And what's wrong with recursive event loops? I think I already explained that one, more or less. Well, since I already showed the example, the other examples I have are much longer. I think it's much better to go to Q&A if there are any questions. And what I do have is a couple of links. You can choose whether you want to put HTTP or HTTPS:/ in front of those things. Okay.
How's yield from?
Hi, why don't you like callbacks?
Sorry. You know, there's a funny thing going. I have no idea where the questions are coming from. Why don't I like callbacks? Because it requires superhuman discipline to write readable code involving callbacks. And if you don't believe me, look at any piece of JavaScript code.
If I want to fire off, say, 2 HTTP connections, which both return strings, and then I wish to yield the concatenation of those, so this is obvious how to do this if they're done sequentially. But I get the impression that tasks are somehow involved in doing them in parallel. But how would I do that? Because you didn't actually cover that exact case.
So you're pointing out a great hole in the presentation, which fortunately is not a hole in the API. That would be terrible. No, there's a gather function in the API, which takes a list of coroutines or futures or tasks, and it waits for all of them concurrently, and then returns you a list of results. And so what you do is you write yield from gather left paren, and then all your different tasks or coroutines. You can just use the coroutines there. They're turned into tasks automatically by gather. And so the yield from waits for the last one to complete, and then returns a list of results, and then you can concatenate them or sort them or whatever you want to.
And that can take a list, not necessarily just individual things, just any amount of stuff?
Honestly, I forget whether it takes a list or you have to use star list, but you can. Let me just look it up. Oh, great, the mirroring. No, I cannot look it up because I cannot type and see what I'm typing at the same time. So my best guess is that particular API actually takes a varargs argument list. So if you already have a list of 10, you just pass it star foo, and you'll get a list of 10 results back, either way.
Hi, just some things I'm trying to understand. Does Tulip provide an essentially asynchronous implementation of UNIX pipes, or is that completely off base?
There is support for pipes, actually. Yes, there is.
Asynchronous?
Yeah. You can. There's actually a high-level operation to spawn a subprocess with all its standard in, out, and error connected to pipes. There are also lower-level operations where you can say, just give me a pipe and I'll make sure I'll care about what happens to the other end. And you can you can use the normal transport protocol style of coding to react to when you can write more data to the pipe or when there's more data to be read.
Am I correct in assuming you don't support UDP broadcasts?
We might be able to add them if you tell me what to do.
I'm QA.
There's actually there's a sort of a backdoor interface where you can create your own socket and configure it exactly how you want and then pass it to the transport.
Right, because UDP depends a lot on timeouts, and it doesn't look like there's a simple timeout functionality built into this.
Timeouts, actually, you mostly will have to program yourself, but it's very easy to program them.
How's yield from different from something like start, join, get result?
You mean with threads?
Well, yeah, I'm just trying to get a better understanding of it. I know you said you couldn't explain this, but
Well, so have you used regular generators in Python?
no.
Yeah, so that
Yes, regular generators. I thought, yeah, I've used generators.
a Python generator, a yield expression or statement, it suspends one stack frame, one Python stack frame. Now that's not a C stack frame. The C stack frame actually disappears, but the Python stack frame, which is a little object on the heap that has like a dictionary of the local variables, you can think of it that way. It parks that stack frame, wraps it in a little object, and then you can resume that generator at any later point by calling next on it, or you can also throw an exception into it. So yield from actually is a for loop. It's compiled to a for loop inside the function that repeatedly yields values from the thing that you call. That sort of, you say yield from some function. Some function actually ought to itself return an iterator, and each of the values that iterator then sends to you as its successive results is being yielded by the frame that contains the yield from.
Yeah, so
And you hear me hesitating, which is why I didn't.
something a little fancier than list of, get generator. Right. If you just you call it list of get generator, getting all of the things immediately, right? But it's doing something better than that.
Yeah, the really clever thing that yield from can do that yield cannot do. So if yield suspends one frame, on the other hand, with yield from, the way if you have a generator which yields from another generator, which yields from another generator, and so on, 10 deep, if the most deeply nested one then yields something, whatever value it yields at the deepest level then gets popped up through all those 10 stack levels, and it gets delivered as the next yielded value to what actually turns out to be the scheduler. The scheduler then sort of looks at what thing was being yielded, and what actually happens is that if you say yield from a future, it sort of yields a list of one element, which is that future itself. So the scheduler then sees the future, says that future is not done yet. It puts it in a queue of futures that it's waiting for, and then it passes control back, sort of out to the event loop. The event loop probably has some other things to do. Maybe there are 10,000 file descriptors, 50 of which are now ready, so it calls the callbacks for those guys. Every time something that sort of gets resumed that way yields another future, it also gets parked in that queue. And so now you have a whole bunch of suspended stacks of generators, stacks of coroutines, each with a future that sort of represents the I/O they're blocked for. And when the I/O is ready, that value is sent back into that stack, and it bubbles all the way back up to the innermost frame, which then continues.
Thank you.
And keeps doing that.
That was illuminating.
I'm sorry.
So Guido, this is kind of like the future of async I/O with Python. Could you talk about like what you envision for users of existing frameworks that want to take advantage of the kind of async world? Like, for example, Django users. Right now they might say go use G-Event and monkey patch the world and take advantage of it that way. What's kind of your vision for the future of these users, existing frameworks?
That's not an easy question to answer, and I fear that for the foreseeable future, there isn't a much better answer than something like that. Asynchronous I/O with explicit callbacks. With sort of explicit yield from will never be completely smoothly integrated with code that isn't really aware of asynchronous I/O at all, and that either depends on there being a small number of threads and not too many long-lasting connections, or just a single thread and completely sequential, or sort of all the old ways of building web servers are really not very well supported by this approach. So there are hacks you can imagine. Certainly one thing you can do is you can have a Tulip-based part of your code and a G-event-based part of your code. Originally, I thought that G-event was so different from all the other asynchronous frameworks that there was no hope, but it turns out that deep underneath G-event, there is yet another event loop, and you don't actually have to monkey patch the world. And so at the event loop level, I suspect that G-event can easily be adapted to Tulip or vice versa. So you could have part of the world that is using the G-event paradigm and part of the world that is using explicit yield from. At that point, however, you're going to have to be pretty smart about not accidentally mixing the two. So I don't know what sort of the right thing to do would be for Django. I expect that at some point, by the time Python 3.5 or 3.6 comes around, different web frameworks that are better suited for sort of working in a more asynchronous world will be invented. I mean, it's quite possible that Flask, for example, which is so much smaller than Django, has a much easier time converting to a new paradigm. But I'm just making one step in what I think is a good direction. I'm not necessarily plotting the complete trip or even knowing the final destination.
So I'm thinking about the what you were referring to earlier about the methods like call, delay, and so forth like that. Could you use those to implement a thread-safe and more concurrent version of what's in the current SCHED module that's in the standard library?
Ooh. Remind me of what that does. I might have written that, but it was probably 23 years ago.
Yeah, it's. I actually was using it recently, and unfortunately, cool. I had to. It's not thread safe, and so I had to end up using something else. But I'm wondering if you have very multi-threaded code. So it seems to me like the building blocks are there. I was just. Are you seeing that too?
Well, I wish I remembered better what the SCHED module actually does, but
it's like cron for Python code, right?
Cron. Oh yeah, totally.
It lets you specify, I want these actions encapsulated by callables, for example, to be executed at certain times. But if you wanted to do it, but what the issue I ran into when trying to utilize this earlier was that I would have long-running tasks that would be kind of blocking on each other, so it would get backed up real fast. Oh,
yeah, that makes sense. Yeah, all the building blocks are definitely there. If you want, if you have a particular action that you want to happen at a certain time, you write that action in the form of a coroutine. You wrap it in a task, and then you write a one-line callback, or you use a lambda that sort of calls that task, creates the task at the designated time. And what that does is the task creation, the constructor of the task runs, and then the callback immediately returns. So your main event loop is unblocked, but the task has been started, and at the next tick, the first bit of code of the task starts running until it hits a blocking point. It yields from a future, and then it yields back to the event loop, and it will take its natural course. And if you have a whole bunch of these guys, and they can all overlap just fine, because the event loop enforces that exactly one callback or stack of coroutines is active at any time.